Hello everyone and welcome to today's lecture. Today I'll be talking about one very nice approach to solving problems in the calculus of variations, and this is going to be the method of finite differences. And the way that I'll present this method is through the use of a very classic problem in the calculus of variations called the Brachistochrone problem, or the problem of finding a path of shortest time. So this problem, the Brachistochrone problem, essentially started as a challenge. It was a problem that was posed in 1696 by John Bernoulli. And the exact challenge reads as follows. He says, I, Johann Bernoulli, address the most brilliant mathematicians in the world. Nothing is more attractive to intelligent people than an honest, challenging problem whose possible solution will bestow fame and remain as a lasting monument. Following the examples set by Pascal, Fermat, etc., I hope to gain the gratitude of the whole scientific community by placing before the finest mathematicians of our time a problem which will test their methods and the strength of their intellect. If someone communicates to me the solution of the proposed problem, I shall publicly declare him worthy of praise. So his problem statement was the following. It says, given 2 points A and B in a vertical plane, what is the curve traced out by a point acted on only by gravity, which starts at A and reaches B in the shortest time? Now, this challenge went out to all of the relevant mathematicians at the time. Newton, Jacob Bernoulli, the brother of Johann Bernoulli, L'Hopital, Leibniz, Lagrange, and it essentially was a 1600s version or 17th century version of a clout battle. Lagrange and all of them submitted solutions, various solutions to the problem at various different times. Newton famously, in fact, supposedly got this problem figured out this problem in about a day, exactly 24 hours. He apparently, according to his biographer, found out about the problem at 4 p.m. Worked tirelessly all night and delivered the problem at 4 a.m. The next morning. So that's a very interesting historical piece of information. Newton also submitted his solution anonymously. However, he was recognized by the other mathematicians. Famously, Newton reportedly said that he did not enjoy to be pestered by foreigners. And what's funny is that his solution was published anonymously. However, upon reading the solution, Bernoulli made this statement in Latin in a response letter, ex unge leonem, which essentially means that he can recognize a lion by his claws. So the solution that we'll present today is actually due to Leonhard Euler, which is in some sense a generalization of many of the methods used for solving the problem originally. The Euler's solution came a little bit later in the 1700s. However, it in some sense generalizes the approaches presented by many of the other famous mathematicians, and it serves as a nice starting point for us in understanding exactly how we're going to do calculus on functionals. So we initially start by supposing that we have 2 points. To make things a little bit easier, we'll start with the origin going out, falling to a point P right here, where P is a distance of L away from the origin and a distance of H away from the origin in terms of its height or its vertical drop. And we're looking for the optimal curve of time or the fastest curve for a marble or a particle, something that has some mass and is falling due to the force of gravity. So we want to figure out what this optimal curve is. So what we first need to do is develop an expression for total time of the fall when falling from O to P along some trajectory where this is going to be some function of the motion along the curve. To do this properly, remember from Calculus 3 or really any calculus course where you consider parametric curves, if you parameterize a curve in terms of the time travel along the curve, the position vector along the curve as a function of time, r, the arrow over it means vector, r of t will be equal to x of t, y of t, where x is the x-coordinate as a function of time and y is the y-coordinate as a function of time. You'll remember from your calculus course that the velocity is defined as the derivative of this position vector with respect to time. It's going to be x prime of t, y prime of t. Now, the arc length along this curve, or the length that you would measure if you say stretched a tape measure along this curve, is defined as s of t. This is a number, and it's specifically the integral from 0 to t of the magnitude of the velocity vector as a function of, say, tau, where I've used tau as my dummy variable of integration here. So this double line thing stands for the norm of the vector, or the length of the velocity vector. Now, taking the derivative of this, or ds dt, gives you a relationship between the rate of change of arc length with respect to time, and this is found just by using the fundamental theorem of calculus, which is basically saying that the derivative of this integral will be the function underlying here. The derivative of the integral of the magnitude of the velocity vector will just be the magnitude of the velocity vector itself. Now, this is a fundamental relationship that we're going to end up using here because it's essentially going to give us the connection between time and displacement in this problem. The best kind of way of doing this is also to kind of simplify here, and I'm going to introduce a slightly simplified notation for the velocity magnitude, and this can be for any vector magnitude, but writing the magnitude or the length of the velocity vector, we know this is always going to be the square root of v1 squared plus v2 squared, because we're going to be using the Euclidean norm for length of vectors in Euclidean space. However, it's nicer, I think, to just rewrite this as just v with no norm notation here when you're talking about the magnitude. It just makes calculations a little bit easier to do. But using this relationship, we can now write the total time of traversal on this curve t as the integral from 0 to t of dt, or differential time along the curve, which will be equal to, under a change of variables, if we change this integral into an arc length integral, the integral from, say, 0 to s at t, and dt here is 1 over v ds. So this is the first kind of step that we need to figure out what the total time is given the input curve. This is kind of the whole idea of what we're trying to do. This integral is just achieved via, say, a u, or better yet, an s substitution here. This is just a u substitution and going from the t integral into the s integral using the fact that the derivative of arc length with respect to time is v. Now, this is not in the final form that we want it to be in. We have one more thing that we need to do to get this integral into an x integral, which is how we're going to kind of approach this functional problem. We want to try and solve for y as a function of x, if at all possible. So we're going to look at how y is related to x here at any given point. And if we say, instead of parameterizing the curve with respect to t, we parameterize the curve with respect to x, this parameterization is going to be given by x, y of x. And that means that the tangent vector to the curve now, this is r prime of x, is the derivative of r with respect to x. This is going to be equal to 1 y prime of x. And so this means then that if we talk about arc length on a curve with respect to this parameterization, the total arc length at any point on this curve going from, say, up to a point s is going to be the integral from 0 to x of the magnitude of this r prime of x dx. And so this means that the derivative of arc length with respect to x, and I suppose that instead of using the notation x here, I'm going to use the notation xi, just because the variable of integration in an integral should never be the same as the variable in the bounds. But if you take the derivative of arc length with respect to x instead of with respect to time, like we did before, you get that ds dx is this magnitude of r prime of x, which is the magnitude of this vector, or the square root of 1 plus y prime squared. So now to convert this integral right here into an x integral, we have that the total time of traversal is going to be the integral from 0 to L, because the value of L is the same as the x value when you're at the ending point, the final point of the curve. ds now is the square root of 1 plus y prime squared over v dx. And so this is a very interesting result. Essentially what we've shown here is that the total time of traversal on this curve and its relationship to y as a function of x, if you can express y as a function of x, then the integral of the square root of 1 plus y prime squared dx over v, whatever that is, will essentially give you the total time of traversal. So given the function y is a function of x, you have that this integral will give you the total time of traversal of your curve. Now v in general, it can be very complicated. It could be a function of x, y, and even y prime in general. Because of the fact that it's the velocity of the traversal, and depending on what forces are active on this falling object, that tangential velocity, remember what v is, it's the derivative of arc length with time. If you have frictional forces, if you have maybe independent forces, outside fields acting on the marble, it could be a very complicated function. So this integral is a little bit more general than what we want to consider in the Brachistochrone problem. In the Brachistochrone problem, we just have one force acting on our object, and that force is gravity. So for the Brachistochrone problem, we actually have a very simple relationship between the displacement and the velocity, tangential velocity. You have that if there's only one force, the kinetic energy at any given point in the fall is going to be directly equal to the potential energy, because gravity is a conservative force, and you have to have conservation of energy. So 1/2 mv squared must be equal to mgh, where m is the mass of whatever is falling, v is the tangential velocity, g is the gravitational constant, and not h but y. Y is the total distance fallen at any given point in time. So this makes a lot of sense, and this gives also a very nice cancellation that the m's actually cancel out in this equation, and we can easily solve for v. So the velocity v is going to be equal to the square root of 2gy. So with this, note that the new functional now for total time, the simplified functional for the Brachistochrone problem, is the square root of 1 plus y prime squared over square root of 2gy. It's the integral of this for any given trajectory function y of x. It's much simpler than the more general formula for propagation under a more general velocity, but this is also going to be a very useful formula for us when we analyze other types of problems, such as, say, light propagation. Notice that the general form these two functionals take. They're definitely functionals because they're dependent on the input function, y of x, and they give us a given value, an output value, that output value being the total time of traversal for the curve. In general, in fact, we can say that this is a general type of functional, actually. We call it the simplest variational problem, and this is typically what's seen in most textbooks on calculus of variations when they define the simplest variational problem. That is, trying to minimize a functional of this form. For the more general scenario, the more general functional here, you have some multivariable function here. It's this entire thing, and I'll kind of really indicate this entire thing right here is just a multivariable function of three things. It's a function of x, y, and y prime. Whereas in the simplified scenario, it's more applicable to the Brachistochrone problem, the integrand is a function of just two things. It's a function of y and y prime. So this is the main simplification when going from the more general case to the more simplified case of the Brachistochrone problem. However, the simplest variational problem is posed for integrals, or I should say functionals, that are integrals of a multivariable function of three variables, x, y, and y prime. So the simplest variational problem is to minimize the functional I of y in the form of an integral from a to b of some multivariable function f of x, y, and y prime. So this is to solve for the y, which minimizes the function y of x, which minimizes this this functional in this form right here. So what I'm going to do now is present two separate, but in some sense slightly equivalent methods of dealing with this problem. And this is called the method of finite differences.